Hello and welcome. Let us start with some simple mathematical facts. Consider a periodic sinusoidal signal with time period capital T. That means frequency f is 1 over capital T and angular frequency omega will be 2 pi f or 2 pi over capital T. Now you can write such a sine or cosine signal as sine 2 pi ft or as cosine 2 pi ft. You may also write them as sine 2 pi t over capital T or cosine 2 pi t over capital T, or even simply you may write sine omega t or cosine omega t. Now let us consider signals of the form sine n omega t or cosine n omega t, where n is a integer 1, 2, 3, 4, etc. That means these signals have frequencies n times larger than that of this sinusoid. Now it is easy to prove that integration of sine n omega t from time tau to tau plus capital T time period will be equal to 0 for all values of tau. That means if you integrate this signal over a complete period of capital T, then no matter at which point you start your integration, the result will be 0. We will write this in this way with this symbol, which means the integration is carried over a total time of capital T, no matter at which point you start your integration. So this is always 0. That is fact number 1, we all know. This is true for all time tau and for all integers n equal to 1, 2, 3, etc. Now similarly, integration of cosine n omega t dt over a complete period of capital T will also be equal to 0. Next, consider the product of sine n1 omega t and cosine n2 omega t integrated over a complete period of capital T. The result will be equal to 0. This is very easy to prove if you take a half common and 2 inside, then you can write it as half integration of 2 sine A cosine B, which is same as sine A plus B plus sine A minus B and you can integrate these two terms separately. Like this, and then the result of this integration will be 0. That is by virtue of fact number 1, and in the same way the second term will also be 0. Okay, now let us consider the product of sine n1 omega t and sine n2 omega t integrated over a complete cycle, then this will be equal to 0 provided n1 and n2 are not equal. You can prove it in the same way by taking half common, then you have 2 sine A sine B, that means it will be cosine A minus B minus cosine A plus B. Now if you integrate these two terms separately, then this term will give us 0 by virtue of this fact number 2, and this term will also give us 0 provided n1 minus n2 is not 0. However, suppose n1 and n2 are equal, then this product sine n1 omega t sine n2 omega t integrated over a complete cycle, which is same as integration of sine square n1 omega t dt, this will give us t over 2. To prove this is your homework, but it is easy to remember because the result will be equal to the total time interval t multiplied by the average value of sine square, and the root mean square value of sine is 1 over root 2, so mean square value or average square value is half, and if you multiply the average value with the total time, you will get t over 2. Now in the same way, you can prove that integration of cosine n1 omega t cosine n2 omega t over a complete cycle will give us 0 if n1 and n2 are not equal, and it will again give us capital T over 2 if n1 and n2 are equal. To prove this is your homework, but you should remember these 3 facts. Number 1, integration of the product sine and cosine gives always 0. However, the product of 2 sine signals integrated over a cycle gives 0 if the 2 frequencies are different, and it gives t over 2 if 2 frequencies are equal. Same thing happens for the product of 2 cosine signals. It is 0 if the frequencies are different, and it is capital T over 2 if the 2 frequencies are same. Now we shall start a new topic, which is Fourier analysis. Consider a periodic signal of any arbitrary pattern you like with time period capital T. Mathematics tells us that any arbitrary periodic signal like this can be created just by mixing sine and cosine signals of different frequencies with different amounts. This is analogous to the fact that light of any arbitrary color can be produced just by mixing 3 primary colors, red, green and blue. Let us call this arbitrary periodic signal as x of t. The frequency is 1 over capital T, and let us define the quantity omega as 2 pi f or 2 pi over capital T. It is possible for such an arbitrary periodic signal that we can write xt as a sum of sine and cosine signals like this. Cosine omega t with amplitude a1 mixed with a2 cosine 2 omega t that has double frequency plus a3 cosine 3 omega t and so on, in general a n cosine n omega t and so on, plus also sine signals b1 sine omega t plus b2 sine 2 omega t plus in general bn sine n omega t and so on. You may also add a term like b0 sine 0 omega t, but sine 0 is 0, so forget that. And also you can add a0 cosine 0 omega t, but cosine 0 is 1, so let me just write a0. So it is always possible to write such an arbitrary periodic signal xt as a sum of cosine and sine signals with different angular frequencies omega 2, omega 3, omega so on, and with different amplitudes or amounts a1, a2, b1, b2, etc. In other words, by controlling these amplitudes or amounts of these cosine and sine signals, you can create any arbitrary periodic waveform you like. Now the big question is this: suppose an arbitrary periodic signal xt is given to us, and we want to know, to create this arbitrary waveform, how much of cosine omega t is to be mixed with how much of sine omega t, and how much of cosine 2 omega t, how much of sine 2 omega t, etc. That means what should be the value of a1, a2, b1, b2, a0, etc., so that this sum will be equal to the given arbitrary signal xt. So to create a given arbitrary periodic signal xt, what should be the values of a0, a1, a2, b1, b2, etc. Now to find these answers, there is a very simple trick. We shall start with the assumption that for some values of a0, a1, a2, b1, b2, etc., it is possible to write xt as a sum of sine and cosine signals like this. So assume that it is possible, and then let us integrate both the sides of this equation like this. So let me integrate the left hand side over a complete period of capital T, and also integrate the right side over the same complete period of capital T. dt, and here also dt. Now the right side of this equation can be split into terms like integration of a0 dt plus integration of a1 cosine omega t dt plus a2 cosine 2 omega t and so on. In general, integration of an cosine n omega t dt, and then this sine terms b1 sine omega t dt plus dot dot dot, in general bn sine n omega t over complete cycle. Now you observe that among all these terms in the right hand side, most of them are 0. For example, integration of cosine omega t is 0 over a complete cycle. Integration of cosine n omega t is also 0. Similarly, sine omega t or sine n omega t gives also 0 when integrated over a complete cycle. Only this one term will survive, and this will be equal to a0 constant, and then integration of dt will be t. So from here that a0t is equal to integration of xt dt, we can write that a0 should be equal to the left hand side, which is xt dt over integrated over complete cycle divided by capital T. So this should be the value of a0. So we have started with the assumption that for some values of a0, a1, a2, it is possible to write xt as a sum of sine and cosine signals, and from that we have derived that the value of a0 should be equal to integration of xt dt over a complete cycle divided by time period, which is same as the average value of xt. So that should be the value of a0. Now let us try to find the values of a1, a2, a3, etc. So for that we shall again start with the assumption that the signal xt can be written in this form, and then we shall multiply both the sides of this equation with cosine n omega t. So the left side is xt multiplied with cosine n omega t, and the right side will be a0 plus a0 multiplied with cosine n omega t, and then plus a1 cosine omega t multiplied with cosine n omega t plus other terms, and here we will get an cosine n omega t, and another cosine n omega t is multiplied, so this will become cosine squared, then plus b1 sine omega t multiplied with cosine n omega t, plus in the same way we will have b2 sine 2 omega t multiplied with cosine n omega t, and so on. So somewhere here we will get bn sine n omega t together with cosine n omega t. So we have multiplied cosine n omega t on the left side and as well as on the right side. Now let us integrate the left side over a complete cycle, and also integrate the right side over the same complete cycle. Let me integrate each term separately like this. Okay, now you observe that among so many terms on the right hand side, most of them are 0. For example, integration of cosine n omega t is 0. Then here we have cosine omega t multiplied with cosine n omega t. The two frequencies are different. Therefore, the integration will give us 0. That is what we have learned at the beginning of our class today. Then, in the same way, the product of sine and cosine is always 0 when integrated over a complete cycle. Again, here sine and cosine gives 0. Only this term will survive. And this will be equal to an constant, then integration of cosine square n omega t dt. Integration of cosine square is equal to 2t over 2 and then an. Now, from this equality n t over 2 is equal to the left hand side, we can write that an is equal to the left hand side, which is here, xt cosine n omega t dt, and then divide by t by 2. So 2 over t here. So this is what should be the value of an. And this is true for all n equal to 1, 2, 3, 4, etc. Which means if you want to know the value of a5, you can calculate it as 2 over t integration xt cosine 5 omega t dt over a complete cycle. If xt is known to us or given to us, you can always calculate this integration. So in this way, a5, a4, a17, all an can be calculated. Now let us try to find the values of b1, b2, bn, etc. So for that, we will again start with the assumption that for some values of a1, a2, b1, b2, etc., it is possible to write xt as a sum of sine and cosine signals, and then we will multiply both the sides with sine n omega t. So then we will have xt sine n omega t in the left side, and the right side will become a0 sine n omega t plus a1 sine cosine omega t multiplied with sine n omega t, then all other terms in the same way, and finally here you will have an cosine n omega t together with sine n omega t. Then you will also have these terms, so plus b1 sine omega t multiplied with sine n omega t plus B2, B3, etc., those terms, and finally we will get Bn sine n omega t multiplied with another sine n omega t, so it will become sine square. Now we will integrate both the sides over a complete cycle like this. Okay, so let me integrate these terms individually. Okay, and then you observe that among so many terms in the right side, most of them are zero. Only one term survives. For example, integration of sine n omega t is 0. Then the product of cosine and sine integrated will give 0. Again sine and cosine, so it will be 0. Here two sine terms multiplied, but their frequencies are different, therefore it will be 0. Only this term will survive, and this will be equal to Bn integration of sine square in omega t dt over a complete cycle, and we know this is equal to Bn t over 2. Now from this we can write Bn as equal to the left side here xt sine n omega t dt divided by t by 2, that means 2 over t here. So this way we can calculate what should be the values of B1, B2 and in general Bn. Let us now see an example. Consider this square wave with time period capital T. So that means this is t equal to 0, this is capital T over 2, this is capital T, this is minus capital T over 2, and so on. Now we want to write this square wave as a sum of combination of sine and cosine waves. Okay, so for that we will calculate the coefficients a0, a1, a2, b1, b2, etc. So let us first calculate a0, and a0 is given by this formula, that is the average value of xt. So a0 can be written as the integration of xt dt over a complete cycle whole divided by 1 over t. Now I can do this integration starting from any point of time as long as the total duration is same as the time period of the signal. So for simplicity, let me do this integration from minus t by 2 to plus t by 2. That means from here to here, one complete cycle. And now you see that x is a odd signal, okay, and therefore this integration will give us 0 because the positive and negative areas will cancel each other. So a0 will be equal to 0. Now let us calculate, say, an, and an can be found from this formula, 2 over t integration of xt cosine n omega t dt over a complete cycle, any complete cycle. So I will do this integration from minus t by 2 to plus t by 2. Now x is a odd signal, cosine is even, so their product will be odd, and therefore when you integrate an odd signal from minus t by 2 to plus t by 2, you must get 0. So that means an will be equal to 0 for all n, actually n equal to 1, 2, 3, 4, all values. Now let us calculate the coefficients Bn. Bn is can be found with this rule. So remember this. This is 2 over t integration of xt sine n omega t dt over a complete cycle. So let me do it from minus t over 2 to plus t by 2. Now you note that this is an odd signal, this is again an odd signal, so the product is an even signal, and therefore you can write this integration as integration of xt sine n omega t dt from 0 to t by 2 whole multiplied by 2, because it is symmetric around the center. Okay, so this becomes 4 over t and integration of xt sine n omega t, but within 0 to t by 2 the value of x is 1. Okay, therefore you can write it as 1 into sine n omega t dt, and this will be equal to 4 over t. Integration of sine is cosine minus cosine n omega t divided by n omega with limits 0 and t over 2. Now this you can write as 4 over t. Take this minus outside, and n omega is again a constant, and inside the bracket we have cosine n omega t by 2 minus cosine 0, which is 1. Now let me put omega equal to 2 pi over t. Here also in omega, in place of omega 2 pi over t, then t by 2 minus 1. Now t cancels here again, so we are left with 4 by 2n pi and cosine n pi minus 1. Now this you can write as equal to 0 if n is even 2, 4, 6, etc., because then this cosine n pi will be 1 minus 1 is 0. I missed this minus sign here. And if n is odd, then this will be equal to minus 4 by 2n pi then cosine n pi will become -1 when n is odd, then -1 minus 1 is -2. So this is if n is odd. So even simply we can write that this is equal to 0 if n is even, and this is plus 4 by n pi if n is odd. So we have found a0, an, bn, everything. So that means this square wave can be written as xt is equal to a0 plus a1 cosine omega t plus an cosine n omega t plus plus b1 sine omega t plus plus bn sine n omega t, and so on. Now a0 is 0, a1 0, an 0, all are 0, and you can write this as b1 sine omega t plus b2 sine 2 omega t plus b3 sine 3 omega t, and so on. Now let me put the value of b1 as 4 by 1 pi times sine omega t, but b2 is 0. Okay, if n is even, then bn is 0. So plus this is 0 plus b3 is 4 by 3 pi sine 3 omega t, then b4 will be 0, then b5 will be 4 by 5 pi sine 5 omega t, and so on. So this way you can express the square wave as a sum of sine waves in this way, with different frequencies and different amplitudes. Let us see if mathematics is correct. This signal is a sine wave, call it x1 equal to 4 by pi sine omega t. Then this signal has a frequency 3 times than the previous one and amplitude 1/3 than the previous one. Call it x3 equal to 4 by 3 pi sine 3 omega t. Similarly, this signal you can call x5 equal to 4 by 5 pi sine 5 omega t. Okay, this has a frequency 5 times than x1 and amplitude 1/5 of x1. In the same way, this new signal is call it x7, which is 4 by 7 pi sine 7 omega t. And then this signal, the last one, green one, call that x9, which is 4 by 9 pi sine 9 omega t. Okay, now if you add x1 and x3, then the result will look like this. This is 4 by pi sine omega t plus 4 by 3 pi sine 3 omega t. Now let me add x1, x3 and x5 together. That will look like this brown curve. Okay, notice that this brown curve has a comparatively more flat top compared to x1 or sine omega t. Now this is x1 plus x3 plus x5. If we plot x1 plus 3 plus 5 plus 7, that will look like this blue curve. And you see, this blue curve has even more flat top. And now finally I will draw x1 plus 3 plus 5 plus 7 plus 9. Okay, and that will look like this orange or light brown curve, which is quite flat compared to a sine curve, and it is somewhat similar to a square wave. In this way, by adding more and more terms, sine 13 omega t, 15 omega t with appropriate amplitudes 4 by 13 pi, 4 by 15 pi, etc., etc., you can create a perfect square wave. You should verify this yourself at home. Now let me give you a homework. Consider this square wave, okay, such that this point is t equal to 0. Previously we took t equal to 0 here, but now we are taking t equal to 0 at the midpoint of this positive half, so that this signal xt, the square wave, is now a even signal, and then this time will be t over 4, this point will be 3t over 4, this will be minus t over 4, and so on. Your task is to find the Fourier series for this square wave. That means find the values of a0, a1, a2, bn, b1, b2, etc. for this square wave, following the approach what we did in this previous example. So today we have learned that any arbitrary periodic signal can be created by combining sine and cosine signals only. But that is not completely true. Any periodic signals cannot be created by sine and cosine signals. For that, the signal should satisfy some conditions, okay, and those conditions are called Dirichlet's conditions. It says that the signal xt that you want to create, if you take the mod or absolute value of that, and then if you integrate it over one complete cycle, then the result should be a finite number. The result of integration should not blow up to a big infinite number. We say that the signal is absolutely integrable, or the absolute value of the signal is integrable. Now, second condition, xt should be continuous, or if it is not continuous, if it has discontinuities or jumps, then at least the amount of jump or discontinuity should be finite. It should not have an infinite jump, and also the number of such jumps or discontinuities within one period should be finite. So we say xt can have at max a finite number of finite discontinuities or jumps. So no infinite jump is allowed, and infinite number of jumps are also not allowed within one cycle. Third condition is that xt can have at max a finite number of maxima and minima within a cycle. So it is not allowed to have infinitely many maxima minima within one cycle. For example, this signal has a maxima here, minima here, another here. Now within one cycle, the total number of such maxima and minima should be finite. It should not oscillate infinitely many times within one cycle. If these three conditions are satisfied, which we call Dirichlet conditions, then for that signal xt, which is periodic, it is possible to create that signal just by mixing sine and cosine signals. Please note that this is a sufficient condition but not necessary conditions. That means if a signal does not satisfy these conditions, then for that signal it may be possible or may not be possible to create that signal by mixing sine and cosine signals. However, if any signal satisfies all these three conditions, then definitely it is possible to create that signal by mixing sine and cosine signals. I repeat, any periodic signal xt that satisfies Dirichlet's conditions can always be created by mixing sine and cosine signals of different frequencies and amplitudes. Now, in the previous example of a square wave, when we calculated these coefficients a0, an, bn, we saw that most of them are 0. All an, a0 are 0, and also bn is 0 whenever n is even. In fact, such situations arise quite often. Let us see that. So this is how we write a periodic signal as a sum of cosine and sine signals. Now suppose x is an even signal, then left side is even, right side should also be even, and therefore all these sine terms, sine signals must vanish. So b1, b2, bn, all bn should be equal to 0. So this is an important fact worth remembering. We can prove it this way. So bn we know is equal to xt sine n omega t integrated over a complete period. So let me take it from minus t by 2 to plus t by 2 and then multiplied by 2 over t. Now if xt is even, this is even, sine is odd, so their product is odd, and when you integrate a odd function from minus t by 2 to plus t by 2, you must get 0. That's the proof. In the same way, suppose xt is an odd signal, okay, which means, that means x of t is equal to minus of x of minus t. In that case, an will be equal to 0 for all n, okay, because the left side is odd, and therefore this even terms, cosine terms must vanish. So a1, a2, an, all of them will be 0. This you may prove by writing an equal to 2 over t integration x t cosine n omega t dt from minus t by 2 to plus t by 2, one complete cycle. And now x is odd, cosine is even, so the product is odd, and odd signal integrated over minus t by 2 to plus t by 2 gives 0 always. So an will be equal to 0. But not only that, not only an is 0, also a0 will be equal to 0 whenever x is an odd signal. Why? Because a0 is the average value of x from minus t by 2 to plus t by 2. Again, this is an odd signal integrated, so this result will be 0. Okay, so if you have x as an odd signal, then a0, an, all of them will be 0. And if x is an even signal, then bn will be 0. Now consider half wave symmetric signals. For example, sine or cosine signal for which this positive half and the negative half, they are symmetric, they are negative of each other, like this, or maybe a square wave for which this positive and negative halves are symmetric, or maybe a wave like this where this negative half is just negative of the positive half. Okay, such signals have the property that x of t plus or minus capital T over 2 is equal to minus x of t. So here this is the time period capital T, that means this is t over 2, and if you consider any point t, then here the value is this much. Now if you move forward or backward by half time period, if you come here, then the value at this point is just negative of this value. Now if a signal is half wave symmetric like this, then then firstly a0 will be equal to 0, number 1. Also an will be equal to 0 for all even values of n, and bn will be also equal to 0 for all even values of n if a signal is half wave symmetric. This is again a very important result worth remembering, and the proof is quite simple. We know an is equal to 2 over t integration of xt cosine n omega t dt over a complete cycle, suppose from 0 to t. You can split this integration into two parts like this. Integration of xt cosine n omega t dt from 0 to t over 2, and then from t over 2 to t xt cosine n omega t dt. Okay, now we will apply a change of variable. Let me keep this first integration unchanged, and in the second integration let me put tau equal to t minus t by 2. If we do that, then x of t will become tau plus t by 2. Now cosine n omega tau plus t by 2. Okay, and d tau and dt will be same, so d tau, and the limit will change from 0 to tau equal to 0 to tau equal to t by 2. Nice. Now first term I will keep as before, and x tau plus t by 2 will be equal to minus x tau because it is a half wave symmetric signal. So here I shall put x minus x minus x tau, and cosine n omega tau plus n omega t over 2, okay, d tau from 0 to t by 2. Now in place of omega I will put 2 pi by t, so that this t cancels, 2 cancels. Okay, then this is cosine n pi plus n omega tau. Now if n is a even number, then this n pi will have no effect, so this you can write as cosine n omega tau only, provided n is even. Okay, and then keep the other terms as it is. This also as before. Or if you want, you can replace this t in the first integration with tau, because that's only a dummy variable. Then you see that the first term and the second term are equal and opposite, so the result is equal to 0. And this is true if n is even. In the same way, you can prove it that Bn will be equal to 0 if n is even for a half wave symmetric signal. Okay, so this is your homework. prove this. Also prove that A0 is equal to 0 if for a half wave symmetric signal. So these are your homeworks. So any periodic signal that satisfies these three Dirichlet's conditions can be created by mixing sine and cosine signals. And these three conditions are not very stringent. Any practical signal that we see in laboratory, almost all of them, they all satisfy these three conditions. They are very easy to be satisfied. So almost any signal can be written as a mixture of sine and cosine signals. Okay, and then we write x of t as a0 plus a1 cosine omega t plus a2 cosine 2 omega t plus an cosine n omega t and so on plus b1 sine omega t plus b2 sine 2 omega t plus bn sine n omega t and so on. Now sometimes it is easier to write this in this form: a0 plus summation over a n cosine n omega t, n running from 1 to infinity, all these terms, plus summation over bn, bn sine n omega t summed over n equal to 1 to infinity. Okay, or you may also write in this way: a0 plus summation n equal to 1 to infinity, then write these two terms together: an cosine n omega t plus bn sine n omega t. Okay, and so these are the different ways in which you can express the Fourier series. This is what we call the Fourier series, the sum of different sine and cosine signals. And you may also write it in this way: a0 plus sum over n equal to 1 to infinity. So divide this with root over an square plus bn square. Okay, and this term also divide it with n square plus bn square, and then multiply it with n square plus bn square. Okay, and then you may write let me define this term as Cn, and let me call this term as cosine theta for some theta, and this term as sine theta for some theta. Then this becomes Cn, and here we have cosine theta cosine n omega t, sine theta sine n omega t. That is same as cosine n omega t plus theta. Let me call this theta n. theta n, because it depends on n. So where Cn is root over an square plus bn square by definition, and theta n, you can write tan theta n is equal to this term sin theta n by cos theta n, so that is bn by an, which means theta n is equal to tan inverse bn by an. So the Fourier series can also be written in this form. That means an arbitrary signal, periodic, and which satisfies Dirichlet's conditions, can be written as a mixture of sinusoidal signals of this form: a0, a constant, plus here we have C1 cosine in omega, C1 cosine in n is 1 omega t plus theta 1 plus C2 cosine 2 omega t plus theta 2 plus dot dot dot. In general, you can write Cn cosine in omega t plus theta n, and so on. Now here this term is called the DC component of this signal xt. This term is called the first harmonic or the fundamental component of xt. Similarly, this term is called the second harmonic, and in general this is called the nth harmonic. My mistake, this here should be minus cos A cos B plus sin A sin B is cos A minus B, and yeah, here also minus, minus and minus. And before I finish, I will just write the three important formulas that you should remember. A0 is the average value of a periodic signal, like this. An is 2 over t integration xt cosine n omega t dt over a complete period, and Bn is 2 over t integration over a complete period xt sine n omega t dt. This is true for all n equal to 1, 2, 3, etc. Here also for all n equal to 1, 2, 3, etc. But this is not true for n equal to 0. Also note, here we have cosine, here sine. Here 1 over t, but here 2 over t and 2 over t. Please do not confuse. So that means almost any periodic signal can be written as a sum of sine and cosine signals like this, and the required amount or amplitudes of sine and cosine, that is an, bn, etc., can be determined using these three rules: A0, AN and BN. Okay, that's it for the day. Well, come back again tomorrow.